And Stefano, please.
Thank you, Maya. So we give the proof of this theorem, and I mentioned that it is something of which there exist many versions, and then we will see a version for approximation of matrices in the context of preconditioning. But once it is important, in my opinion, to have the flavor of this kind of proof. Okay, so here is the proof. Okay, so you have phi n from C01 into C01, which is linear and positive. I give all the steps. So we recall linearity, phi n of alpha f plus beta g will be alpha phi n of f plus beta phi n of g. And then if f is non-negative, then phi n of f is non-negative. Okay, quite standard. We have seen are of this kind, and in other kind of spaces, not in C01, also the Toeplitz operators are linear and positive in the sense which is specific in the related vector space. So first of all, we observe that from the fact that phi n is LPO, linear positive operator, we deduce in one line that phi n is monotone. What I mean, if f1 is greater than f2, you take two continuous functions, one larger of the other, then this is equivalent to tell that f1 minus f2 is larger than 0. Consequently, by positivity, so maybe we give here name alpha and beta, that is beta, phi n of phi1 minus phi2 is larger, f2 is larger than 0. Therefore, by linearity, phi n of f1 minus phi n of f2, so I used the linearity of phi n is larger than 0, which is equivalent to phi n of f1 larger than phi n of f2. Oh, so we have an ordering on the initial domain. We find the same ordering in the images. So phi n of f1 is larger than phi n of f2 if f1 is larger than f2. So this is a kind of direct consequence of linearity and positivity. And as a consequence, it is evident that phi n is also isotone. What I mean? So it is clear that f is between the modulus of f and the modulus of f. This is kind of trivial. So by monotonicity, which we just proved, phi n of f is between minus phi n of modulus of f and phi n of modulus of f, which is the same thing of saying that phi n of f modulus is less than phi n of modulus of f. So this is isotonicity. Oh, by the way, now there is a check for understanding if you are sleeping or not. There is something that you recall very basic that works like this, that you should know independently of me, of course. So try. Nothing in your mind? You never encountered the adjective isotone?
Well, I must confess, no.
You not. But it's funny because it's something very basic.
Maybe, but maybe I don't know the name.
Okay, so think to phi n like the integral. So the absolute value of the integral of f is bounded by the integral of the absolute value of f. So the integral is isotone. And why this is so? Because the integral is a linear positive operator. The integral of a linear combination is a linear combination of integrals, and the integral of a non-negative function is a non-negative. So it's a special case of linear positive operator. So this relation, which is written here, you know from a special, very special linear positive operator, which is the integral. Okay? But this is a general property for any linear positive operator. So the modulus of phi n of f is bounded by phi n of modulus of f. Now, with the monotonicity and the isotonicity, which are consequences of being linear positive, we can give the proof of the Korovkin theorem. So pay attention to the fact that phi n is a sequence of linear positive operators. So we have only this, plus the fact that there is a convergence on these three stupid functions. And if you have a convergence on these three stupid functions, then you have a convergence for any f, also a function which is continuous but nowhere differentiable. So this is kind of a strange theorem, because usually in functional analysis, you prove a property on a dense subset, and by some kind of continuity or stability, you deduce some property on a larger set. But you should have a property on a dense subset. Here it is not dense, it is made by three functions. So it means that a linear space which is three-dimensional decide a property for an infinite dimensional space, which is kind of very, very surprising. It was so surprising that when I learned, I was 25 years old, for the first time this theorem, I thought it was false. So I spent 1 week trying to prove that it was false, but it's not. Okay. So I want to emphasize that is a highly non-trivial theorem, even if it is even if it is very simple to prove. It is kind of elementary deduction. So from this assumption on the test function, we can say that phi n of t to the power j evaluated in x, j equals 0, 1, 2, we have only this stupid function. It is exactly x to the power j plus some error, which I call epsilon n j of x. And since there is uniform convergence, I assume that epsilon n j x infinity norm goes to 0 as n tends to infinity. So I have written in a different way this assumption on this test, which is finite. By the way, this test is called Korovkin test. Is a test on a finite number of functions, only 3 in this case, and should be this exact 3 function. Now, we have this. This is just rewriting the assumption. We want to prove that phi n of f minus f of x can be bounded by some epsilon for n larger than a certain n of epsilon and for any x in 0, 1. Okay? So for any epsilon larger than 0, we find n larger than n epsilon such that this inequality is true. So we start to work with this inequality. Okay? So for n epsilon, there exists a number n of epsilon such that this is true for any n larger than n epsilon and for any x uniformly in 0, 1. Okay? So we work with the quantity phi n of f of t in x minus f of x, and take into account that we only know that f is continuous. Now we observe that this can be written as phi n of f of t in x minus. Look, here there is 1 times f of x, but 1 is exactly x to the power j when j is 0. So here there is 1. So 1 I can write as phi n of 1 of x minus epsilon n 0 of x times f of x. Okay, so I've found a complicated way of writing 1, but which is useful. Okay. Now this is equal to what? Phi n of f of t of x minus f of x for phi n of 1 of x plus epsilon n 0 x times f of x. Now I write this in an interesting way using linearity. This is something outside, I put inside, and then I use linearity. So this is phi n of f of t minus f of x, x plus epsilon n 0, x times f of x. By the way, think to this as integral. If you have an integral of something multiplied by a function on x, you can put the function of x in the integral. Okay, this does not is not something crazy. You can do, and we have done here. Now we use something simple, triangle inequality. So this is phi n of f of t minus f of x in x plus u. Now there is the modulus of that, but the modulus of that is bounded by the product of the infinity norm. One of these is uniformly converging to 0, and the other is the infinity norm of a function which is continuous on the interval 0, 1. So is something that we can govern very well. Okay, so for sure there exists some n bar of epsilon such that the infinity norm of x times this infinity is less, for instance, of epsilon divided by 3. for any n larger than n bar epsilon. Okay, so from the moment on, I will consider that this is less than epsilon over 3, because this converges uniformly to 0. So does not depend on x, only on n. Okay? So again, we repeat, phi n of f of x minus f of x is bounded by phi n of f of t minus f of x plus epsilon divided by 3 and n larger of a certain n bar epsilon, uniformly for any x. Okay? Now we use isotony and we put inside the modulus. So this is bounded by phi n of modulus of f of t minus f of x in x plus epsilon divided by 3. And now we want some clever majorization of this and for using the monotonicity. Now we look for a clever measurement of modulus of f of t minus f of x. Okay, remember that both t and x moves in 0, 1 independently. Okay, now since f is continuous in 0, 1, which is a beautiful compact set of R, then f is uniformly continuous. So for any larger than 0, there exists some delta larger than 0 such that t minus x less than delta implies f of t minus f of x bounded by n. But notice that this relation with the small n is true only when t and x are close. Okay, so which is the idea? Here is the genius idea of Korobkin. So the proof is really elementary, but here there is a very clever idea. So this is the point which is important for the proof. So f of t minus f of x is bounded by what? How do you call the characteristic function of a set? So the function which is equal to 1 if something belongs to the set and is equal to 0 otherwise. Can I call this with this symbol, key? Okay. So the set is p minus x bounded by this delta. You see? In t. So when t minus x is bounded by delta in t, then this difference is bounded by n. So I can put n. But when this is not, then I do not have a clever way, but I can tell f of t plus f of x using the triangle inequality. So I should put 2 times infinity norm of f. Do you agree? So when this inequality is satisfied, then the difference is bounded by n. When the inequality is not satisfied, the worst case can occur, and this worst case is 2 times the infinity norm of f. Okay, you agree with that? So, but this is 0, 1, so I forget of this. I just put n. So I have bounded this by 1. This is bounded by 1. And so I put just ni. So I simplify. Then now is occurring the genius idea, so pay attention. So this is 0 or 1, okay? But this is bounded by what? T minus x divided by ni to the power 2. Why? Because when this inequality is satisfied, then t minus x divided delta is larger than 1. So when this is satisfied, this is equal to 1, but t minus x divided delta is larger than 1. So I can replace with the square, which is even larger than 1. You understand? When this is 0, I don't care about this because I'm replacing with something which is non-negative. This is a very genius idea, but it is important that you understand it properly. So look, this is the characteristic function of this set. So when the relation is satisfied, this function is equal to 1. But when this relation is satisfied, it means that t minus x is larger than delta, which is equivalent t minus x divided delta larger than 1, which is equivalent t minus x to the power 2 divided by delta square larger than 1. And since this is equal to 1, I can replace by this, which is larger than 1, is what I've done. When this relation is not satisfied, this quantity is equal to 0. So it is for sure majorized by this. And this is really a genius idea because the majorization of this is reduced to a quadratic polynomial. If you expand with respect to the dummy variable t, then if you expand, it is just a linear combination of 1 t and t squared. So we can use what we know on the Korovkin set. Okay, so now I continue using this and this. So remember that this argument in modulus is bounded by this. So the one. Sorry. Bounded by, so we made a lot of steps and we arrived to phi n of modulus of f of t minus f of x in x plus epsilon divided by 3. And this is bounded by monotonicity by phi n of ni, which can be chosen small as we want, plus 2 infinity norm of f t minus x to the power 2 divided by delta square, plus epsilon divided 3 in x. Now we stop majorizing and we make computation. So phi n of ni is ni phi n of 1 plus 2 infinity norm of f divided delta square. And here there is phi n of t minus x to the power 2, which is t squared plus x squared minus 2tx in x plus epsilon divided 3. Okay? Now this is phi n of 1, but phi n of 1 is a test function, converges to 1. So this can be bounded by 2 times ni. Remember that ni, I can choose it as small as I want. Okay? Plus 2 infinity norm of f divided delta square. And now here the miracle will occur. This is phi n of t square in x plus x square, because this is the general variable, it's not the dummy variable. Remember that this is like an integral in t. X is the global variable, it can go outside. Phi n of 1 of x minus 2x phi n of t in x plus epsilon divided by 3. And this is equal to 2n plus 2 infinity norm of f divided delta square. And now we go here. Remember that phi n of 1 is 1 plus something going to 0 uniformly. Phi n of t is x plus something going to 0 uniformly. Phi n of t square is x square plus something going uniformly to 0. So this is what? Phi n of t square, x square plus epsilon n2 of x plus x square multiplying 1 plus epsilon n 0, because this is t to the power 0 x, minus 2x times this, which is x plus epsilon n 1 of x plus epsilon divided by 3. So 2n plus 2 infinity norm of f divided delta square. And here we can make the computation. So there is x square plus x square times 1, and then minus 2x times x. So the x square disappear. So this, and this disappear. So you obtain epsilon n2 of x plus x squared epsilon n0 of x minus 2x epsilon n x plus epsilon divided by 3. So it is a combination of errors going uniformly to 0, multiplied by bounded function 1x squared and minus 2x. So this goes uniformly to 0. Because these are constants and this depend only on n, because the convergence is uniform. So this is E bounded by 2n plus epsilon divided 3. I can choose that this is small of epsilon divided by 3 plus epsilon divided by 3 for n larger of n of epsilon. And this is less of epsilon, choosing n equal to epsilon divided by 6. And I can do that because remember that n was the constant of uniform continuity. So I can choose, there is for any n, there exists blah, blah, blah. So now I choose n equal to epsilon divided by 6. And here it becomes exactly epsilon. So there are versions for pointwise convergence. There are versions in any compact set of R. There are versions on compact set of R to the power D. There are versions for L1 convergence, for LP convergence. So there are whole books on this Korovkin stuff. So Korovkin started, and then there are people that build their career on the Korovkin theorems. So since, in my opinion, it is a relevant theorem because it's a genius theorem, I wanted you to show this. And also because it's the basis of the matrix algebra approximation that we see now. Okay, so where we arrived, D. E1. So matrix algebra precondition. So we choose the preconditioner in belonging to a matrix algebra related to a unitary transform. So the algebra will be AUN, the set of all matrices in MNC, such that X is equal to UN d UN star d diagonal and UN star UN equal to the identity. So we have already encountered one of these algebra. For UN equal to Fn, A Fn is equal to circulants. Okay, so the circulants are a matrix algebra related to a unitary transform. But then there are the omega circulants with omega of modulus equal to 1. Also these are, for any omega of modulus 1, algebras related to a unitary transform. Then there are at least 4 sign transform algebras, and these are used in PDEs, but also in signal and image processing, and the same for the most known, which are 4 cosine transform algebras. In all of this algebra, the only thing that changes is the UN. UN is a specific matrix, which instead of being related to the Fourier functions is related to sine function, cosine function, or some modification of the Fourier by some parameter omega. Then there are at least 4 Hartley transforms, algebras. These are sine plus cosine transform, and they are very much used by engineers because engineers do not like, and these are completely real algebras. Then there are the wavelet transform algebras. And this is just a small list. So this class includes the circulants that we have seen, but it includes also a lot of other algebras. So it makes sense to study in this general framework. So given A belonging to MNC, given, let's see, AUN, our matrix algebra, as preconditioner for A, we choose PUN of A. So this can be read as preconditional, but also projection on this algebra, defined as the arg min, so minimized, which minimize this distance A minus X in Frobenius norm, such that X belongs to AUN. You know the Frobenius norm? So now some preliminary for understanding the notation. The Frobenius norm of y, or y in M and C, is nothing else than the sum of yjk modulus square j and k from 1 to n to the power 1/2. So, what is this stupid norm? Is one of the preferred norms for numerical analysts because it's simple. You take the matrix and you consider it as a unique huge vector of size n square, which contains all the entries, and you use the Euclidean norm. Okay? So easy to compute. And for this reason is used in numerical analysis. It is easy to compute, but it has also beautiful properties. If Q is unitary, so remember Q star Q is equal to the identity, then Q represents an isometry. So a transformation that does not change the Euclidean norm. So for any x belongs to Cn, the norm of Qx, the Euclidean norm, what it is? The Euclidean norm of a vector, if you remember, is the square root of y star y. So you take the vector, you put horizontal, multiply, you make the scalar product, and you make the square root. But then this is also equal, since y is qx, to qx star qx. So it is equal to x star qx. But q star q is the identity because q is unitary. So this is equal to x star x, which is the two norm of x. So two norm of x and two norm of qx are the same. So unitary matrices are isometries. Okay? But since the Frobenius norm is the Euclidean norm of a very long vector with all the columns of y, what we can deduce? That the Frobenius norm of QA, where Q is unitary, is equal to the Frobenius norm of A. Why? Because if you multiply Q from this side, you are multiplying all the columns by a unitary matrix. So the two norm of all the columns remains unchanged. And so the Frobenius norm, which is the norm of all these columns altogether, remains unchanged. You see this? And if you reason in the same way, but not by column, but by row, you will discover that also this is true. Okay? So, consequence of the definition and of the fact that unitary matrices represent isometries. This property has a name, and the name is that the Frobenius norm is unitarily invariant. And there are, as for Korobekin, whole books on unitarily invariant norms. The Frobenius norm is the most beautiful from the computational point of view unitarily norm you can find. Unitarily invariant means that you can multiply your matrix from the left or from the right by a unitary matrix, and the Frobenius norm does not change. And why this is important for us? Because our algebras are related to a unitary transform. So this is the point. So now let us see the consequence of the fact that the Frobenius norm is unitarily invariant for our problem. Okay, so for our problem, what we have I want to consider PUNA, which is the minimizer of norm of A minus X Frobenius for X belonging to AUN. So this means that X is equal to UN DUN star for D diagonal. Then I take this quantity and I write explicitly A minus UN DUN star Frobenius. But then UN is something that I can put in evidence. Frobenius. So in some sense, since the unknowns, I have to find the D that makes this minimal. So in D, there are the unknowns. So I isolate the unknowns. But UN and UN star are unitary. And the Frobenius norm is unitarily invariant. So the norm of this is equal to UN star AUN minus D. And I have to minimize of all the diagonal. So when I compute the Frobenius norm of this difference, outside the diagonal, I cannot do anything because D is diagonal. But on the diagonal, I can do something. So the optimal choice, that is the minimizer, is the opt equal to the diagonal part of UN star AUN. And since this is true, your PUNA is equal to UN, because should be a matrix in the algebra, diag of UN star AUN, UN star. This is the optimal choice given your matrix A for the preconditioner, in the sense that it minimizes the Frobenius distance. Okay? It is already the 2 o'clock, but I say just one thing more and I stop. When UN is equal to Fn, that is, for circulant matrices, this Frobenius optimal preconditioner is also called, so you find in the literature also with the name Tony-Chan preconditioner. Especially when you deal with tablets problems. For sparse matrices, Ucle, Benzi worked a lot on this preconditioning. Okay, I stop and we resume in 15 minutes. Okay?
Yes, it's done. Stefano. Yes.
Okay, thank you, Maya. So we arrived to the last hour. Okay, so given A belonging to M and C, given A UN matrix algebra with unitary transform, the Frobenius optimal preconditioner or approximation, because this is approximation theory for matrix sequences, is computed as P(un) of A equal to UN diagonal part of UN star A UN UN star. Okay. And this Frobenius optimal is unique. We have seen from the formula before. Now, if you look, this expression tells you that P(un) from M and C to AUN, which is a subspace of M and C, is an operator. For any A, you have this projection in the algebra, which is defined in this way. And P(un) is linear. You see from start. If instead of A, you have a linear combination of matrices, you can put outside the constant and you have the linear combination of the projection. So P(un) of alpha A plus beta B is equal by the formula P(un) of A plus beta P(un) of B. And P(un) is also positive. If you start from a matrix which is Hermitian and non-negative definite, so if A is equal to A star and is non-negative definite, then UN star AUN is still Hermitian and non-negative definite. You make the check. And it is a special case of what is called the Sylvester inertia law. Therefore, the diagonal part of un star AUN is a non-negative diagonal matrix. And finally, PUN of A, which is UN, this diagonal, which is non-negative, is Hermitian and non-negative definite. So also the projection, the Frobenius optimal approximation for any matrix algebra with unitary transform defines a linear positive operator. In particular, if A is equal to Tn of F, so it's a Toeplitz matrix generated by F, then PUN of Tn of F is a composition of two linear positive operators. So you can define this from L1 minus pi pi into AUN subset of M and C, and this is another LPO, linear positive operator. For this special linear positive operator, there is a Korovkin theorem. For this specific matrix valued, because it's matrix valued, LPO, there is a special Korovkin theorem. First of all, we give just a short definition of clustering. Probably you have seen with Maya already, but I give in my language. So if you have Xn sequence of matrices of increasing size, so Xn belonging to M and C, and also M of some Dn of C, which grows with N. This, in particular, in the multi-level problem, it is good not to have just N, but some D of N. But here, for simplifying, I prefer to write Mn of C as a strong cluster at alpha in the eigenvalue sense, if and only if there exists a constant let's see, for any epsilon larger than 0, there exists a constant depending on epsilon such that the cardinality of the eigenvalues of xn such that lambda j of xn minus alpha, the cluster point, larger than epsilon is bounded by C epsilon. So this means that if you have n equal 1 billion, 1 billion minus C epsilon eigenvalues are very close to alpha, their distance is less or equal to epsilon, and only few of them are outside this small disk centered at alpha. Okay? This is the definition of strong cluster, or if you follow Tirtishnikov, proper clustering. This is Tirtishnikov language. And he is an academician of science in Moscow, and all academicians of science in Moscow are allowed to invent their own language, and the other are invited to follow. Okay, so it's called strong clustering or proper clustering. When xn is made by positive definite matrices and alpha is equal to 1, the use of the conjugate gradient will produce only C epsilon plus 1 iterations for convergence. There are other mild assumptions, like the fact that the outlier should not go close to 0. And these are Axelson-Lindskog estimates. Okay, so the strong clustering is quite important. And in fact, you check it also for GMRS, even if the convergent theory for GMRS is much more complicated because it depends also on the conditioning of the eigenvector matrix when it exists. So it is not that easy. But in practice, checking the clustering at 1 is a way for having a good indication if the method will go in a fast way or not. Okay, so given all this language, now I present you the Korovkin theorem for in the Toeplitz setting. Okay, and then we see some practical thing, otherwise we are completely lost probably. So, theorem. So let a UN a sequence of matrix algebras with unitary transform. So growing n, it can be a sequence of circulants. Okay. So if you like AUN, as before, x equal un the un star, the diagonal, and un star un equal to 1. Okay. Now, this is the take into account that the Frobenius optimal approximation of any matrix is a linear positive operator. So if you compare with the standard Korovkin theorem, you don't find the assumption that the operator is linear positive, because we consider an operator which is linear and positive by construction. So you do not see this assumption. So consider a single matrix, very simple, Tn of ei theta. So the Toeplitz matrix generated by this Fourier monomial. So it will be 0 on the diagonal and 0, 0, 0. Here there is 1, 1, 0. So it's very, very simple. Okay, is the transpose of a Jordan block. Okay, the transpose of a basic Jordan block. Now is the equivalent of the Korovkin test. But while the Korovkin test in the theorem we have seen for function requires the check with the 3 functions, here only one function, e to the I theta, and one matrix is considered. So is even more striking than the original Korovkin theorem. Okay, so compute the eigenvalues lambda j of Pun of Tn e to the I theta. Okay, so you take the Frobenius optimal approximation of this and you compute the eigenvalues, which I recall you are just un star Tn e to the I theta un in position jj. So it looks complicated, but this is just a check with a very, very simple matrix. Okay, if maximum over j of lambda j Pun Tn ei theta, so these eigenvalues that we have computed, minus e to the I 2 pi j over n, so a sampling of this function uniform on the unit circle is bounded by a constant divided by n, C constant. Then, and here is the striking Korovkin type result, for any f continuous and 2 pi periodic, so continuous and 2 pi periodic, you have the following, that Tn of f, the matrix that we want to approximate, minus the preconditioner Pun of Tn of f, is strongly clustered at 0. Okay, so if you make a check on one stupid matrix, you have a consequence to a huge set of Toeplitz matrices generated by functions which are continuous and 2 pi periodic. So it is really in the style of Korovkin. P1. If in addition f belonging C2 pi is also positive, so that TNF is positive definite, then PUN of TNF minus 1 Tn of f. So the preconditioned matrix is a strong cluster at 1. So in the light of the Axelson-Liskov result, I expect a constant number of iterations. And now you can see all the picture, because we have seen that if UN is the Fourier matrix, then the Toeplitz vector product costs O(n) log n. The solution of a linear system with the circulant costs O(n) log n iterations, operations. And in addition, thanks to this strong cluster at 1, the preconditioned conjugate gradient in this specific case needs only a constant number of iterations. So constant number times n log n will tell you that we have a solver, an iterative solver, within n log n arithmetic operations, which was the question by Benjamin at a certain point. So it is at that point we had only a n log n algorithm for matrix vector product. Now, thanks to this matrix version of the Korovkin theorem, we have also a solver, an iterative solver, at least when f is positive and 2 pi periodic, which is of global cost of n log n. Okay? The power of the theorem, so the theorem is finished. The power of the theorem is the assumption which is very simple to check. But this is something that I tell to you. So in order to convince you, let's make a check. Let us make a check just for convincing ourselves. Okay? So I will take the case of circulants and I will make the check. So I will take this matrix, the Frobenius optics, we will check this assumption, and then if we check this assumption, we have automatically this result and this result. So we have a lot. So we check on a single matrix with a specific f, and we have for any f which is continuous and 2 pi periodic. So we have a huge result starting from a unique assumption. Okay? Let's make this assumption just for having the flavor on how these Korovkin results work. So UN equal to Fn. So AUN equal to circulants. Okay? I have to take Tn of e to the I theta, which, as I said, is the transpose. So there is one here on the subdiagonal and the rest is 0. Now the generic circulants, so x belonging to AUN, x is done in this way. There is C0, 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 then C1, 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 till Cn minus 1, and then everything is repeated. So here there is Cn minus 1, Cn minus 1, and here there is a C1. Now, think to the X optimal, the one that minimizes the distance from this. Which coefficient C0 you think it will be the optimal one? If I make the difference between this and this, which is the optimal coefficient C0?
0.
0. Now you have C2 here. Which is the optimal coefficient C2? C2 is here and then is here. Which is the optimal coefficient C2?
1.
C1 is in the position of 1. C2 is
Okay.
here. Huh?
Oh, yeah. So 0 is
0 again. So the same for C3 until Cn minus 1. Just because in the original matrix, these parameters are where the matrix is identically 0. And then you have to consider C1. But C1 is tricky because there are n minus 1 elements which are equal to 1, and then C1 appears also here where there is a 0. So which will be the optimal C1? So C1 is a strange guy that should please n minus 1 guys equal to 1 and 1 guy equal to 0. So which will be his solution? You can see geometrically. So the 1 is weight n minus 1 and the 0 is weight 1. So if you make this convex combination, the optimal C1 is 1 minus 1 over n. That is n minus 1 over n. So the PUN of Tn of e to the I theta is 1 minus 1 over n that multiplies this matrix 0, 0, 1, 1, and since should be circulant, it is like this. So it is 1 minus 1 over n times the matrix that we call Z1, the generator. But we computed the eigenvalues of the generator. So you have to go back in the slides, but you can do in any moment of computing the eigenvalues of this matrix. And the lambda j of zeta1 are e to the I 2 pi j over n. And you see what kind of thing we have to verify. That this lambda j minus exactly e to the I 2 pi j over n is small. So what we have to verify that max over j, so if the eigenvalues of zeta1 are this, the eigenvalues of 1 minus 1 over n times this are 1 minus 1 over n e to the I 2 pi j minus n minus e to the I 2 pi j over n. And this maximum, what it is? If you put in evidence this, which is the same, the modulus is 1 minus 1 over n minus 1. So is max over j of 1 minus 1 over n minus 1, because the modulus of this, which can be put outside, is equal to 1, which is 1 over n, which satisfies the assumption. We know exactly the C. which is equal to 1. Then we have finished. If after this check, we know that the Frobenius optimal approximation by using circulant of Toeplitz works for any function f, which is continuous and 2π periodic. So if you have a new algebra, no big computation. You have to consider this. You have to compute the Frobenius optimal approximation, seeing what happens to the eigenvalues, check this assumption. If this assumption is true, everything is wonderful. If this assumption is false, then the algebra does not work. So it is really a simple check. And using this Korovkin theorem, we made the check for all the known algebras for checking which are good for Toeplitz and which are not. So it's a kind of meta theorem, because the Korovkin theorems are like meta theorems. They are not simple object, but allows to check many situations. Okay. Did you follow the check? More or less, or not? No, at the end, it is surprisingly simple, but the notation is clear, which is not so friendly. So it seems that this beast is just terrible, but in this specific case, it can be computed by hands. The minimization problem is really, really elementary, and you have to do on a simple matrix. This is the advantage. So if it is another algebra, again, you have to compare with this. So it is very simple. So it is very likely that also the approximation in the algebra, the optimal approximation in the algebra, is sparse, almost as the original matrix. So many things will be zero, and then the computation will be very simple. And if the test succeeds, then this is okay for any kind of matrices. Okay. So if you change algebra, so instead of Fn, you take another algebra, then the check is absolutely of the same type. So few words on the band Toeplitz reconditioning. So using LPO concepts, we have proven what is in the left. So if f is real valued almost everywhere, and small m is the essential infimum of f, capital M is the essential supremum of f, then in the assumption that m is less than m, otherwise it is stupid, the lambda j of T and F belongs to m over m, to this open set. But there is even something more, that lambda minimum of TNF minus m is asymptotic to 1 over n to the power alpha if f of theta minus small f, small m, the minimum, is asymptotic to some theta minus theta 0 to the power alpha. So you know that if small m is equal to 0, these matrices will be ill-conditioned with condition number growing as n to the power alpha, just because the function is a 0 of order alpha. So the alpha should be positive. But there is something even more, if F is non-negative and G is non-negative, define small r as inf of F over G and capital R as sup of F over G. So consider the ratio and assume the non-trivial case that small r is less than capital R. Then lambda j of Tng to the power -1 times Tn of F belongs to R, and lambda j, lambda min of Tng -1 Tnf minus R is asymptotic to n to the power alpha if F over G of theta minus R is asymptotic to theta minus theta 0 to the power alpha, alpha greater than 0. Why this is important? First of all, there is something very strange. We know that matrices do not disasters, but in such a case, you take Tng to the power -1 times Tn of F, the eigenvalue behave exactly like F over G, which is a kind of miracle. So they stay in the interval given by the range of F over G. And in addition, they mimic also the extremal behavior of F over G. So if F over G minus R is a 0 of order alpha, then the convergence of the minimal eigenvalue to the small r is like 1 over n to alpha. Here I talked about band, but here nothing is written about band. But you have to understand the computational sense of this theorem. So if you have some f, which is with the infinite Fourier, Tnf is dense and is such that f over g is in a small interval, for instance 1, 2, and g is a trigonometric polynomial, then Tn of g is a band Toeplitz matrix. So you are preconditioning a dense Toeplitz matrix with a simple band Toeplitz matrix, which computationally makes sense. And if this interval is small, then the number of iterations will be a constant independent of n, and each iteration will cost again order of n log n. The solver of order n log n, which is alternative to the solver with matrix algebra preconditioners. Okay, so this is the order, and all of this is a consequence of the, again, of the theory of linear positive operators. It is a theory very, very general and also very elegant. One can prove a lot of things without much effort. So now, just an example. In the approximation of the Laplacian using the Singh-Galerkin method. Not important if you know or not, which is a kind of spectral method. So it gives you a superlinear convergence of the discrete solution to the continuous solution. The following dense matrix appear as coefficient matrix. It is of Toeplitz type and is the Toeplitz generated by theta square. Okay, so this is a kind of dense matrix because theta square is not a trigonometric polynomial, so all the Fourier coefficients appear. Now, theta square divided by 4 sine square of theta 2, this miracle function, is between 1 can prove very easily using the relation between theta and sine of theta, and pi square over 4. And the mythical discrete Laplacian delta n, 2 minus 1 minus 1, 2 minus 1 minus 1, is exactly the Toeplitz matrix generated by 2 minus 2 cosine of theta. We have already described this, which is exactly, by the way, Tn of 4 sine square theta 2, because this is a trigonometric manipulation of the same quantity. Okay? But this is bounded, and for this there are optimal solvers which are linear. So if you use this theorem where f is theta square and g is this 4 sine square theta over 2, then you have that this dense matrix can be preconditioned by this band matrix having all the eigenvalues which are between 1 and pi square over 4, which means, roughly speaking, that with the 7, 8 iteration, you reach the solution of your linear system with a very good precision. So again, the solver will cost only on log n iteration because you are able to use a band precondition. By the theorem on the right of R1, we deduce that lambda j of delta n minus 1 times Tn belong to the open set 1 pi square over 4 for any n. So n 100 or n 1 billion is the same, which implies that PCG is the solution within On log n arithmetic operation. I asked for more time, but I will stop 2 minutes before, just because the topic which is left is again big. I want to talk you about some approximation of differential equation with variable coefficient, where again a kind of technique like this band preconditioning works well, and again you have linear positive operators. But really there is no time and it makes no sense to run as a crazy. So I stop here and thank you.
Thank you, Stefano.
And of course, if you have questions, I've put really a lot of material, but the idea is to give you as much as possible, trying to be clear, but you are not forced to learn everything. If you have curiosity, you can ask now, or you can reach me by email. I'm available. We can make meetings like that. So I'm available for you if you like. This is the message.
So,
Maya, you are always with this face crying for some questions.
well, no, I'm thinking that we should try to summarize. I don't know how the PhD students are feeling, but you can see.
So the summary is the following. I have presented how to make fast matrix vector multiplication with tablets. Okay, so you can do by O(n) log n, and by the way, we have seen the fast Fourier transform, the general fast Fourier transform, the working with the circulants and whatever. So this can be done in n log n arithmetic operation, which asymptotically is much smaller than n squared. And in addition, we have seen that the constants are very small, so that this can be used in practice. And in fact, this is used in practice. But solving within O(n) log n arithmetic operation a circulant linear system and multiplying within O(n) log n arithmetic operation with tablets is just a way of telling that when you use your precondition and the GMRS or precondition and conjugate gradient, every iteration costs O(n) log n arithmetic operation with a small constant. Now it remains the problem of understanding how many iterations. And if you prove that the number of iterations is a constant, bounded by a constant, depending only on the precision that you desire for the solution of your linear system, then you have obtained an optimal solver. That is a solver whose cost is of order O(n) log n, which is exactly the cost of the direct problem of multiplying a matrix by a vector. And this was the sense of the last part of these lectures. So about the Teplitz-Korovkin theorem and about this band preconditioning, because these two techniques, one using clustering, the other reducing to a small positive interval, are a way of obtaining a preconditioned conjugate gradient, which theoretically can be proven to converge within a constant number of iterations. So if you put together constant number of iterations and O(n) log n cost per iteration, you have an optimal solver. And this is funny because when I'm telling in such a way, I remember that I learned the notion of optimal solver and of dividing this notion as a constant number of iteration plus optimal cost per iteration, that is the cost of the multiplication of a matrix, coefficient matrix by a vector, by a paper of Neitcheva and Axelson, which was published in a stupid Bulgarian proceeding. I mean stupid because, you know, we have journals which are a journal, a big H index. This was really something almost shameful because it was the Plovdiv conferences with the Drumi Bainov, which was more a person interested in business than in science. But in Latin, there is the expression ex falso quod libet, which means from something negative, you can obtain also something positive. And this is true in logic. When you make an exact reasoning starting from a false statement, you can arrive by chance to a true statement. So in this rubbish of the Plovdiv conferences, I found this beautiful paper by Axelson and Neitcheva, and I learned the notion of optimality. Then I put it in my PhD thesis, and then I'm teaching to students. So this was an example. So thank you, Maya.
Well,
Well,
Yeah.
So, plus a personal amarcord.
Life is interesting.
Oh, very much.
Yeah, so I want to say something more in this direction, which Stefano summarized. If you remember when we were talking about preconditioning, I told you that at least my opinion is that the strongest way to construct optimal preconditioners is if we can construct an operator which is spectrally equivalent to the operator we are dealing with. And then we discretize. And since we have optimality on operator level, it doesn't matter how we discretize, it will be optimal whatever we do. Now you see here the same idea. We have a framework which is very general, based on algebras of matrices and functions. And then this gives you a tool to construct also optimal preconditioners, which are very, they can be quite different between each other, but they still lie in the same class of objects where the theory is valid. And of course, we go sort of down and we try to figure out matrix-dependent preconditioners, problem-dependent preconditioners, but they are weaker, or they may be very efficient, but they cover a small part of the problems we may face. So I think it's very, from this course, you should see the theory, and you should, as one of the goals, I think you should be able to judge correctly when you face such a problem, what to choose and where to look for methods which could be suitable, right? And also try to see that if you look at the literature, you can see techniques which improve other techniques by adding a method parameter, some method parameter, or one or two or something. Then you have to give exact recipe how to choose them, because the user doesn't like method parameters. And so the best methods around, like you can see, they are parameter independent in many cases, which is very good. They're easy to use. And if I have a method parameter where I need some optimal alpha to minimize some spectral radius somewhere, and I have to run my problem just to find the optimal alpha, I have to run 1,000 times, I doubt that the user will use this method. At least it will not be preferred, because the time you waste to find the optimal parameter is much larger than the time to take another method where you do not have problem parameter, method parameters. So I think you should think in those terms, because obviously we cannot cover all the cases. We cover some which are typical, and we give the flavor of the properties they may have.
Of course, Maya is talking from the point of view of the correctness of science. Then there are a whole, like a huge amount of people which are publishing a preconditioning technique depending on hundreds of parameters, which is good for publishing and maybe for having a career. But they are not useful from a practical point of view. And I know that Maya, when she receives as a managing editor of the journal such papers, she's kind of desperate, because it is a wave of parameter-dependent preconditioning papers, which are good for publishing, but somehow they are really useless as advance in knowledge. And I have a personal memory about this, about this preconditioning, because when I started in Pisa doing that, my professor told me that preconditioning was not elegant, was a kind of technicalities to find the good approximation, but without theory. So at that time it was more or less like this. So somehow I took this message, and my contribution was to try to make a general and also mathematically beautiful theory of the preconditioning. And somehow we succeeded, because with this possibility of using function, you can use all the beauty of the theoretical mathematics for analyzing at least preconditioning, and also for finding new ones. And then things evolved, and there are many contributions. And what Maya said is absolutely important. Often the problems are parameters dependent, but you don't want to add new parameters when you look for a precondition. The precondition should work in the more robust possible way.
Yes.
You discovered that Maya and myself influenced each other very much. So I started with their papers, and then we collaborated. So it is really a long story.
Yeah, which was, yeah. I want to say something more. We are a little over time, but I hope you bear with me. So I have put on the website, the course website, the assignment for the first preconditioning part. It is on complex symmetric matrices and two kinds of preconditioners. Because I wrote the project new, maybe there is something which is not very clearly written. Please let me know. Just read it and see how it is. I have uploaded Stefano's hands-on and his assignment. So the hands-on he is suggesting contains, there are quite a number of tests. And I really advise you to go through, because they illustrate
At least to try, because some
yes.
of them are theoretically not easy.
So yeah, so you are very welcome to ask, as he said, me or him or something, and then they are very helpful for the assignment. And so the assignment takes a couple of typical cases where this theory he was presenting is applicable. And again, if there is a terminological question or any other question, just ask. Don't waste too much time to figure it out, and just ask first. I have put some deadlines for the two. There is one more which is left. The deadlines, I don't know, you have teaching load and so on. I'm not going to make a big question if you are delayed, but for your own good, it's not good to it's not very advisable to delay it, because one forgets. So that's what.
And within this evening, I will send also the scan of the of what I presented.
Yeah.